But do you have the thing already?
So that's the thing. So theoretically, you should not use that one because that one's
Okay.
There might be echoes and stuff.
Yes, understood. Yeah, that's true. But okay. Right, what time is it? When they were first doing that, simulations. So I created replicas of this and had it for it, and second, like put balls. And so the guidelines then is keep up 20 people. So also suburb. You know what's the type of filter? The type of filter in the air conditioning. Oh, yeah, this one. What is it? All not that anybody paid any attention to discussions. So if they wanted to have in class, recording, people. All right, so let's get going on this. Welcome, everybody. Today it's my pleasure to introduce our colloquium speaker, Alberto Krone-Martins from University of California, Irvine. Alberto started his higher education first by getting graduate in classical piano at the Conservatory in São Paulo. And then he decided he'd like to play different kind of keyboards. So he first got a bachelor's degree in physics at the University of São Paulo, followed by master's in astronomy, followed by the PhD jointly with the University of Bordeaux in France. And then he was at the University of Lisbon, Portugal, until 2019, where he moved to UCI. Alberto was working on Gaia since about 2006, I think, and mostly on issues of data processing, data analysis, which is really the project that we're describing today, on which we've been collaborating for the last few years. He's very active in astroinformatics, astrostatistics community. He is a chair or co-chair of the 2000 Astrostatistics Initiative, then International Astroinformatics Association, and probably one of the top young researchers in the whole field of astroinformatics worldwide. So without further ado, Alberto.
Thanks, George, and thanks everybody for this invitation and for the opportunity to talk a little bit here to you and to discuss a little bit with you about a different way to use Gaia, right? So as many of you know, Gaia was created to study the Milky Way. Gaia satellite that was created to study the Milky Way. But we have been using Gaia, and actually we changed the satellite itself in certain parts of the software that's on board of the satellite as well, to allow Gaia to study objects that are outside the Milky Way as well, as galaxies and gravitational lens quasars. That's the topic of today's talk. So it's obviously impossible to talk about everything that we have been doing in terms of the gravitational lenses with Gaia, but at least by the end of this talk, I would like for you to have a grasp of at least about why we are searching for more gravitationally lensed objects with Gaia, how we are searching for those objects, and also about a little bit about the future and about exciting prospects about using different types of computers that I'm going to talk to you a little bit in the end of the talk to search for new lenses or to solve machine learning problems. So starting with the motivation then. So why we are looking for these objects? So to me personally, one of the important reasons is also because they are aesthetical beauty. Obviously, it's not only because of that. Gravitational lenses are amazing probes of gravity, right? But they also bring to us aesthetical beauty. And this is one of the very well-known gravitational lenses. It's called Gaia and Cross. And this is one of the lenses that we discovered in the past few years in our lens program. That's what we call the Riga's link shot. It looks like a link shot, right? Anyway, so the other reason why we are looking for those objects has to do with their utility. So those objects are also, as I was mentioning, very useful to study gravity, right? And to study other types of extragalactic phenomena. Right? So to understand why they're useful and how we can use them to study gravity and dark matter and cosmology, it's important just to have a grasp of why they exist, why those objects exist. So what happens is that when you have a background quasar, and in the middle of the way, in the middle of the path between the quasar and the Milky Way or the Earth, you have an intervening galaxy that bends space-time, and then all the photons that will never arrive in the Earth, since space-time is bent, they are going to be bent. So, and then we are going to be creating, if there is a small disalignment between the galaxy and the quasar and the Milky Way and the Milky Way and the Earth, we are going to be forming several different images. In this case, we are forming 4 different images, right? So a telescope from the Earth is going to see 4 or 2 different images. It's not 4 or 2, it's going to be 3 or 5, but the central image essentially disappears. In the end, we end up seeing 4 or 2 images, right? So why they are useful, right? So one of the reasons why they are useful has to do with the fact that they are variable. So a quasar, so the quasar varies along the time, right? So it's varying like a random walker, essentially. So if we observe the light curve of those quasars, of one quasar, it's going to look like a random walker. Since the gravitational lens is creating multiple images of the quasar, we are going to see essentially the same light curve in the different images. However, the photon path in the universe is different for each one of those images. And moreover, the gravitational pull is also different between the light of each that create the photons that are creating each one of those images. So those light curves, they are not exactly aligned at the same time. So if you try to realign the light curves of the different images, we are going to see that there is a small difference between what's happening in one image and what's happening in the other image. This is what we call the time delay. And it happens that by measuring this time delay, if we can model the rest, if you can model essentially the geometry of the source and of the lens, right? There's a term here in this modeling that appears, and this term happens to be one of the holy grails of modern astronomy, right? And this essentially, this term here is foundational, or the Hobo constant. For the students around, this is an extremely important constant that essentially gives us scales in the universe for observational people. Like it's thanks to this constant that you can transform relative things that you're observing in absolute measurements, like distances or ages and time. Right? And it happens that nowadays this constant is under significant tension. So this plot here is showing for a bunch of different experiments the different values of the Hubble constant. Each point here is one value that was measured plus the error bars, right? And the interesting thing is that for experiments derivations of the Hubble constant based on the early ages of the universe, we have a certain value of the Hubble constant. Meanwhile, for almost all the other probes of the Hubble constant, we have another value that's higher than those values that are probed in the beginning of the universe, right? So there is a tension that nowadays, the tension between the values in the, that are obtained by indirect methods and the direct methods is already at the level of more than 5 sigma, right? And so gravitational lenses then are a powerful probe for measuring the Hubble constant and for obtaining better values for the Hubble constant and trying to assess if this method is due to some sort of this difference is due to some sort of systematic effect or for new physics that are still lacking in some point in some region here that link what we're seeing at the beginning of the universe to what we are seeing now. And one of the interesting things of gravitational lenses is that we can probe gravitational lenses along the lifetime of the universe, right? So we can probe gravitational lenses in very high redshift and if in relatively low redshift as well. Anyway, so however, the error bars of the lenses are still high. They are still huge compared to the error bars that you have from CMB probes. Anyway, so one reason then to study and to discover more gravitational lenses is essentially to obtain better estimates for H0 for the Hubble constant. However, there is another reason to study gravitation, to discover new gravitational lenses. I was talking about the word here, systematics, right? One of the systematics that exists among gravitational lenses is the other reason why we want to discover more lenses. Because these values of the Hubble constant, they are essentially driven as well by the matter distribution on the galaxy that creates the lens. So what do you think that it would happen with a lens if you had the smooth galaxy plus several clumps of dark matter around smaller clumps to the order of 10 to the 5 to the 10 to the 6 solar masses around that the galaxy that's creating the lens? What's going to happen essentially is that the images that, are not going to be in the position that they would be for a dark matter halo that would be blue. You essentially would have additional astrometric and photometric shifts in the positions of the image that we're observing. And here is something that's interesting for Gaia, because those astrometric differences are at the order of a few hundreds of microarcseconds for a typical halo of 10 to the 6 solar masses, right? And Gaia is going to observe all of the lenses, not the one or two, but all the lenses in the sky to the level of a few hundred microarcseconds. So we will be able to probe structures to the level of 10 to the 6, 6.5 solar masses, not in one or two lenses that are observed either because they're radio out and we can target in VLBI, or because we can have time capture of series or that, but for all the sources in this time. Okay, so this is the second reason why Gaia can be a powerful machine for this as well. But the problem in both cases is that those sources are rare. So those are not sources that human time took 40 years to discover 200 global lenses and about 50 quad, so quadrant image lenses like this one. Okay? So it took like 40 years to discover only 50 of one class and 200 of the other class. And this is one of the reasons why we have been using like Gaia that's going to have HST-like resolution, but not for one source or for one region of the sky, but for the entire sky. Okay. And as many of you know, Gaia was created to study stars. But this is a map that we're going to be seeing later this year that shows galaxies that Gaia has been observed. So this is 1.8 million Gaia. So those are input galaxies that Gaia has been observed, where you can already start seeing some structure, like in the Hubble Though Gaia is expected to be complete after the redshifts, very low redshift, like 0.2, 0.3, right? But it's going to be complete. And those galaxies are going to be seen to the level of 200 milliards seconds in the PSS. So we're going to be able to study the morphology of all those galaxies with very high resolution. Okay, but obviously among the galaxies, we are going also to be observing quasars. So, Gaia is observing all the quasars from the sky up to magnitude 20.7, more or less. It's expected to be complete up to magnitude 20.7. Although Gaia EDR3, so the Gaia that we have now, and this is also true for Gaia data release 3, that's going to come in June this year, it's not complete even for the quasar, for the lens itself. So in a lens like this one, so this is the Einstein cross. In a lens like the Einstein cross, where you would expect to see those 5 images, so the 4 images of the quasar plus the galaxy itself, in EDR3, you can only see those 2 sources. Meanwhile, we are losing those 3 sources. So any methodology that's used to create or look for new objects or for new lenses in Gaia needs to take into account incompleteness as well of the sources that are being observed. Okay. However, Gaia will provide like 2.6 thousand lines of the QSO. So we expected, assuming lambda CDM, to be able to observe and discover 2.6 thousand lines of the QSO. Just compared to barely 250 that we know now. Right? So that's a tenfold increase in the number of lenses by the next. So therefore, it's going to be probably 2025, 2026, something like that. Right? Anyway, and this is for between 2 and 4 images. With 4 images, Gaia is expected to cover 250 lenses. Out of the 50, 60 that we knew a few years ago, nowadays we know between 60 and 70 lenses. Also thanks to the project that we have been running in this past few years. I'm sorry, can I just bring some more? So how we have been doing this then? So Gaia has been transferring downlinking data to the ground, and then we publish the catalog. At each publication and each data release of Gaia, what we do essentially is we downlink the entire data release into the RAM of a machine. So it's the entire, or Gaia lives in the RAM, it's not living in the disk for us. And in this machine, we cross-match with CRTS, ZTF, WISE, FunStars, and essentially we can have access to anything that provides a SAP plus an ADQL interface. From this cross-match, we run several different methods. I'm going to talk a bit about 2 of those methods a little bit later. But the idea is that there are several methods that are going to be used to select candidates. Those candidates, which in the beginning we had 2 million sources, are going to produce a list of about 1,000 candidates that are going to be inspected by humans. So we humans, in the GraL group, we inspect the images and the data for about 1,000 objects. Out of those, initially 2 billion sources, right? And select about 100 candidates that will go to telescopes where we are going to be performing spectroscopic confirmation, right? So the most important telescopes that we have been using are essentially TEC, the ISO-NTT, and now the VLT. But we have been using significantly as well Gemini South, SOAR, .bta, and in the beginning of the program, we were using HALO as well, right? But the main machines that we have been using are essentially TEC, NTT, and the VLT. So after the spectroscopic observations, all the results look back into the machine learning systems again. And this is a closed loop. And more important than this being a closed loop, this is, we are not, so this is a closed loop, that is not ignoring the human knowledge. We keep human knowledge inside the loop all the time. So there is a human feedback, continuous human feedback in the program, selecting the data that's going to be observed, right? And in a certain way, what we're doing here, it's not very different from what you have been doing when you're using Google in your daily life, or when you're using Amazon to buy stuff, right? It's a recommendation system that is changing even the way that you think. It's a system that helps you to think into things that perhaps you will not be able to think. So it's we are using AI here not as artificial intelligence in a certain way. We are using AI as augmented intelligence. So we are just increasing the capability of us as astronomers to go beyond of what we would normally do, what we would normally be able to do otherwise. But we are not replacing a human by an algorithm. We are using the algorithm just to help humans to take better decisions, okay? Anyway, as you saw, there are three big families of methods here. So the one big family of methods is using just Gaia data. It's purely based on Gaia, which is using only astrometry and photometry plus supervised learning. The other family uses astrometry. Astrometry is everywhere, but plus photometric time series, especially from CRTS and ZTS. And the final family of methods uses imaging data from imaging surveys like pan-stars, mostly pan-stars at the moment. And it's based on unsupervised and supervised learning alike. So I'm not going to comment a lot about all those methods, but I just wanted to give you an overview of what we have been doing in terms of those methods, especially in terms of those two methods. So the photometric time series and the imaging data. For the supervised learning over Gaia data, the situation is relatively simple. What we do essentially is we create simulations of hundreds of millions of possible lens configurations. And so essentially we vary the mass of the galaxy and the impact section between the quasar and the galaxy and things like that. And we produce around 106 billion Gaia simulations of observations of lens equation. And then we add, and this is the important thing, over the simulations. So this is not just the simulation of the lens. This is the simulation of the lens, considering how Gaia would observe the lens, with all the possible errors that Gaia would introduce over the lens. So when we train a machine learning method, we train a machine learning method with a biased set to avoid mismatches in the domain of the training and the application of the method that was trained, okay? So this is the most important thing that we do in this part. But for the photometric time series, the second family of methods is based on photometric time series and the photometric time series as well, but especially the photometric. This is a very dear concept or principle that was actually developed a few years ago here at this building. The idea is to use entropy to classify candidates of state. So imagine we just saw in the beginning of this talk that a quasar, if you observe a quasar photometrically, like the time period, is going to be a random walker, essentially, right? So if you have a pure non-lensed quasar, this is going to be a random walker. If you have a lens, what you're going to be seeing, if you could resolve the lens, would be the same random walker repeated, except for observational errors, but with the time delays. If you cannot resolve this equation, what you would observe would be a time series that would be the addition of the same random walker time delayed. Since it's the same random walker time delayed, what will happen is that you're going to introduce the information again and again in the same time series. And this essentially will make the stochasticity of your random walker to drop. So this is a principle that we verified a few years ago using data from Catalina, from CRTS. What we're seeing here is the population of the PDF of the entropy of the unresolved, already known quasars, lensed quasars in Catalina, and in blue, the entropy of all the other quasars. And so we are simply seeing that this, right? So that the entropy for the lenses that you cannot resolve is going to be lower than the entropy of the overall population quasar. This is obviously not completely pure, so this is true for all the quasars. The thing is that you can always have a quasar and a star, right? And since the light curve of the star has a very low entropy, when you add together the quasar and the star, the entropy is also going down. So this cannot be used alone to select quasars and select lenses. But this is one important information to select candidates for lens quasars. And this is the amazing thing, even if you cannot resolve those quasars or those lenses. Okay, so this is one of the principles. We have been using many other signals in the selection of those quasars those lens quasars based on time series, not only the entropy. The entropy is the most important signal, but we also add the Fourier power spectra, and this is good because it helps us to get rid of stars, especially if the stars have some periodicity, right? Slopes and the significant frequencies in the power spectra, and correlations between the astrometric time series and the photometric time series. All those features, we then pass through a transformation that's a simple linear PCA. Why simple linear PCA? Because we want to keep the understandability of what we're doing. After you do a PCA, you can actually understand how the PCs were built based on top of those features, right? You can know why a certain object is being selected as a lens candidate. And then we select the dimensions after the PCA based on Anderson-Darling tests between the lens and non-lens population of quasars in each one of those dimensions. So we simply select the dimension for which there is a large discrepancy between lenses and non-lenses. And then we build a big model that's called an ensemble model that's essentially mix different types of machine learning methods to produce a classification. So this is how we select candidates based on time series. Now, the third family of methods is based on images. And the idea to select a lensed system based on images has to do with another feature space that we call wavelet space. So the idea behind the wavelets is essentially to decompose a signal into multiple scales. So this is one example of a galaxy, a classical example of a galaxy being decomposed into multiple scales. So this is the original image. And then in the first scale, you have only the very high frequency structures. And then in the second scale, you have a little bit broader structures. And then at each scale, you have broader and broader structures. So this image here is actually the addition of this scale plus 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 this scale. So why wavelets are interesting here? For two reasons. First, because assuming that you have a lensed quasar that you cannot perfectly resolve. So what's going to happen is that you're going to be your optic is going to be barely resolved. But when you decompose in multiple scales, you're going to be able to see that you have power spreading into larger scales than the PSF, essentially. Meanwhile, a pure quasar that's non-lensed and completely unresolved will be always kept within the PSF. So there will be no leakage of signal outside the scale of the PSF. So if you know the wavelet transform of the PSF, you can easily get in objects that are a little bit bigger than the PSF, even if you cannot resolve them, right? So this is another signal that we use. And the second reason why the wavelet transforms are important here, it's because they can bring us to important features, to important characteristics, which are translational and rotational invariance. So if we compute the wavelet transform, and then you compute how much power do you have in each one of those scales, it doesn't matter if the image is upside down or if you're not in, the image is not in the center, if the quasar is not in the center, so you automatically get translation and rotational invariance by going to the power spectra of the wavelet power spectra, right? And we also use Fourier power spectra and another thing that's called butterfly distance that I'm going to comment in a few minutes in another context, but it's essentially how hard it is to transform one image into the other. And this is the space that we use to perform the classification here. So the problem here is that we still have a very high dimensionality. We are talking about 1,000 dimensions if you add all those features. Meanwhile, we only have 200 lenses to train. So we only know 200 and something lenses, right? So you cannot train a method if you have 1,000 dimensions and 200 examples. So how do we solve this problem? So again, the simplest way to solve this problem is what we have been doing until last year, which is doing Anderson-Darling tests and reducing, selecting the dimensions for which the lenses and non-lenses population would be the most discrepant. And then using some very simple hierarchical clustering to select the candidate. What we are doing now is essentially selecting a subspace. And this is going to be the last part of the talk today in a few minutes. And we select a subspace using actually quantum computers. And this is what we have been using since essentially November last year. And the final method that we have also been using is simple autoencoders, but not directly on the images. Again, autoencoders operating on top of the wavelet transform of the images. To simplify, once again, so this is essentially replacing the convolutional layers of the autoencoder. And as we add as well the power spectra, it brings us as well rotational and translational invariance. Anyway, so these are all the methodologies that we have been using in our lens program so far. So all those methodologies were created in the past 3 years and a half. They were all tailored, 3 years and a half, 4 years more or less. They were all tailored to search for new lenses from Gaia and Xray. Although it's Gaia data, this can be applied to any data except for the astrometry part, right? So this will be applied to LSSC data as soon as it starts flowing. This will be applied to field data as soon as it starts flowing as well. Anyways, but you could always ask, right? So, okay, interesting. And this by itself is an interesting research program for computing, like for informatics. But for astronomy, the answer is, have you been discovering anything using those methods, right? So this was the first lens that we discovered using the only Gaia data and the pattern matching based trained on simulation. And this was the first lens quasar that was discovered before an image even existed. So we discovered this lens quasar only based on the Gaia positions. So what you're seeing here is essentially the Gaia positions of 4 detections, right? And based on the angles and the difference of magnitudes between the Gaia astrometry, we selected this as a good candidate for a lens. Then we went to CAC, and it was confirmed as a lens. Ever since, we have been discovering many more quadruple image quasars. So those are a few. Those are 12 lens quasars that we have already published. There are 3 other quads that were not yet published that were discovered now last year. And well, perhaps this will be 3 to 5, depending how we fit the lenses or the candidates. And we have also been discovering several doubles. So those are 8 doubles that we discovered. This is probably not a lens, this is probably a binary QSO. We could not detect the deflector. The other one, we could detect the deflector. This one, this red emission here looks like a deflector, but it's actually a star that was found exactly in the position where the deflector could be, right? But this is a star that just appeared over there. And these were the doubles that we discovered essentially during the pandemic. So those are the pandemic doubles. So there are 44 new doubles. I'm not completely certain, but perhaps this was one of the largest catalogs of lenses that were discovered in one single moment of time, right? Clash, for instance, that was a catalog that was searching for lenses using radio. They actually surveyed almost 20,000 quasars to discover a handful of objects, a handful of lenses, right? Well, here we are discovering 44, and this number here, it's significant. First, because these are just the northern ones. We're not counting, I'm not adding here the southern ones without images yet. And the second thing is that this is 44 discovering, let's say, you can exaggerate, 3 years. It took us 40 years to discover 200, and we discovered 44 in 3 years, right? And the rate of discovery is not expected to go down. It's only expected to go up, actually. We've improved the resolution for the new data releases of Gaia, and with as well the new methods that we have been developing, because we never stop developing new methodology. We're always adding new methodology to the selection of new lenses. And this is a very nice project for many students as well. There are many students doing some part of those methods that enter in our continuous loop. And there are those other 11 objects that may be a lens or a binary quasar. We don't know yet. We could not detect the deflector. This one, there are a few ones that could even be quads, but they are quads that are so tight that we could not yet observe, not even with Gaia, the 4 images, right? Perhaps there are quads as well among some of those, like this one. Perhaps it will be a quad in a fold configuration or something like this. Anyway, among the sources that the lenses that we discovered, one remarkable example that I really like is this one. It's the third largest QSO lens in the sky. So this is 11, essentially 11 arc seconds. So this is a gigantic lens in the sky. But more than this, one of the interesting things of this lens quasar is that we were not believing that this was a lens. So it was the end of the night in the NTT, and I said, oh, we're not going to observe it. This is not a lens. We decided to observe, and in the end, it was a lens. But it's amazing that nobody discovered this before, right? So this lens here could be already found in the pulse plates from 85, and even with the deflector, can be seen. Sorry, and yeah, now it's still late. But not even from 85, you could go to 54 and already see the 4 images over there. Right? And this is way before, so this is before Martin Schmidt actually detected quasars. Right? Anyway, if this had been discovered by that time, Einstein would have another reason to smile, and Vicky perhaps would be a little bit less grumpy. At least would have a reason to be a little bit less grumpy, because he was the first person to suggest that an extragalactic object could create a lens, and that would be observable soon, right? He said soon. It was not, it took 20, 30 years to be observed, but at a certain point it was observed. But this could be observed while he was still alive. Anyway, so ever since, together with the discovery of new lenses, we have been also following up those lenses in other wavelengths, like in radio. So this is just one example of one of the lenses. So this is one of the lenses that have been followed with the DLA. We are also following with Attica, the southern lenses we go to Australia to observe. And also for the dark matter studies, especially, we have been following with Spectral Series, Gemini, GMOS, and VLTUs as well. So especially the VLTUs in the wide field mode to be able to take into account in the modeling the shear terms that are added by galaxies, other galaxies in the line of sight. And we have also been following all those lenses with Xray, and in particular, we discovered, which is probably the brightest lens, the brightest QSO in Xray in redshifts above 2 as well. Anyway, so this has been so far the discoveries that we have been doing with in this program in GraL. Now I would like to talk just a little bit about the future of how we can improve on the discovery. What is the major problem here for us at the moment to discover more lenses? As I mentioned, one of the biggest challenges for us is the dimensionality of the parameter space. We are working with very high dimensions, like thousands of dimensions. And meanwhile, we have 200-300 lenses to train the methods. So you cannot train the methods in all those dimensions. So if you're using supervised learning, then you cannot train. You could simulate the lenses. And it's very simple to simulate the astrometry, but it's very hard to simulate everything else. Like, can you simulate reliably the life curve of a quasar? Of all the quasars, of all the population of quasars? You can simulate, but not as reliably as we could simulate the astrometry of a lens, right? So we avoid using simulations for the other method. We only use simulation for the astrometry and for the pattern. And then we could use perhaps semi-supervised learning and unsupervised learning. That would help, but the problem of operating very high dimensional space and calculating distances between points in very high dimensional space would persist. So this is a problem. This is not the mathematical problem. This is a problem in computer science in general, right? So how we can solve this problem? There are two options. Either you transform your dimensions and you compress your dimensions in a parameter space that is transformed, where you try to preserve interpretability. This is possible. This is not the path that we are taking now. The path that we are taking now is, okay, I am in a parameter space that I understand, that I can interpret. How can I select a smaller volume of this parameter space where the classification will be optimal and still I will be able to train with a small number of points, right? So essentially, the question is how you can find the best subspace to solve a given classification problem. So to explain to you what we're doing, I think that it's good to go back to our intuition and how projections work. So suppose then that you have this data here. So your data lives in a two-dimensional parameter space, okay? And you have those two blobs of points. So now, suppose that you cannot work in two dimensions. You need to work in one single dimension. What is the single dimension that you would choose to work to solve a classification problem? So the most extreme cases in this toy problem would be either projecting in X or Y, right? And if you're projecting X or Y, you would have this distribution or this distribution. So intuitively, if you had to select one of those to solve classification, which would you select? Anyone? Any guess? Not? Okay. Probably this one, right? Because, yeah, it seems more spread, and I can see two peaks. So you could draw a line here and say, okay, this is a class and this is another class. Easy, solve it. So intuitively, we know how to solve those problems and select them. Now, how you can do this, not intuitively, but mathematically, right? It happens that there is a good mathematical distance that you can actually calculate to help you selecting those dimensions. And this is what we call a Wasserstein distance. So a Wasserstein distance is essentially, so computer scientists, they like to call this distance the Earth mover distance. So this is essentially how hard it is for you to take a pile of dust and to move somewhere else, essentially. Or statisticians and mathematicians like to call it the Wasserstein distance because, so given that you know how to optimally transport a probability function, what is the optimal transportation cost between a certain PDF into another PDF? So how hard it is to transform one PDF into the other PDF. So intuitively, if we go back to our classification is, I have two classes, and those are my two PDFs. I want to select projections to solve my classification problem, where this cost here is going to be maximum. So it's going to be very hard to transform one class into the other, right? And then, so now intuitively, we know how to select in one dimension. Obviously, you can do this in 2 dimensions. You can do this in 3 dimensions. So you can do this in any number of dimensions that you want. The thing is, if you have 1,000 dimensions, you're not going to do this in all the possible combinations of 1 to 999 dimensions, right? How can you then create a problem where computing a small number of Wasserstein distances, you would be able still to find an optimal for your entire problem, for your entire classification problem? So simply, by first getting all your one-dimensional projections, calculating Wasserstein distance in 1 dimension, getting all your 2-dimensional projections, calculating Wasserstein distance in 2 dimensions, and then setting up an optimization problem that looks like this. So this is essentially, you would essentially write, the Q here is the Wasserstein distance projected in the dimension I. Meanwhile, the QIG is the Wasserstein distance projected into the dimensions I and G for all the possible combinations of I and G's of your 1,000 dimensional space. And the X's, they encode, they are binary variables. They are going to encode if you're selecting or not that distance to solve your classification. So they can be 0 if you're not selecting that distance, that dimension, or they are going to be 1 if you're selecting that dimension to solve your classification problem. Okay? So essentially, after you set up this, you have a problem that's simply you need to find what is the best vector of x's, where you're going to be 0s or 1s, that are going to allow you to solve the classification in the most optimal way. How you can solve a problem like this? So we can solve problems like this in very small, for very small sizes in classical computing. It happens that when you look to this problem, there are lots of problems. There are lots of problems inside the problem. One of the problems that this is discontinuous, right? So these are binary variables. It's hard to calculate derivatives and to follow derivatives and things like that. So this is a combinatorial problem. Do you remember your quantum physics classes and the Irvine model, where this looks a lot like the Hamiltonian for an Ising model, where those x's are the spins, right? And here you have coupling constants and the electromagnetic and magnetic field overall, the lattice. So this is essentially what quantum annealers were created for. And it was very, very fun when I was actually building the problem like this, when I started and said, oh, this is exactly what I wanted to solve. So this is a quantum annealer computer, which is essentially a quantum computer that's going to find the state of minimum energy for problems like this. They are called quadratic unconstrained binary optimization problems. Okay? So essentially, by using quantum annealers, you can find the optimal states of those functions. And this is what we have been doing since November last year to select the dimensions. Then after selecting the dimensions, we moved to a classical computer to solve the actual machine learning problem. So the dimensional selection, the dimensionality selection is performed in a quantum computer. And then we move back to the classical to train a support vector machine, a random forest, and so on. So, right? But using the dimensions that were already optimized. Okay. So based on this method, actually, we selected. I think it was three targets that went to the telescope in November. So they went to check in November, and out of the 3 targets, we actually discovered one of those targets ended up being a new lens. Right? So this is a lens. So this is not very beautiful, but it's a double lens. So you have the blue emission here and the other blue emission here. Those are the 2 Gaia sources, and then you have a reddish emission around. That's certainly the lens in Gaia. And so this was the first. Probably this was the first discovery, as far as I know, of anything that was made with the support or with the help of a quantum annealer, as far as I know. Anyway, so that's it. I think that's it. So on behalf of this entire group of people that have been working in this gravitational lens search program, I would like to thank you, and I'm ready for questions. Thank you.
So questions for Alberto?
With the dragon type, we're looking at forces that are actually very far separated. And so therefore the time series for DCF or or anything like that is spatial resolution.
Yeah. So
have you done a generic search for regions around Quasar to see if there are correlated individual time series which get us together?
So, well, yeah. So, so your question was about the time series and the correlated time series between astrometry and photometry, right? So the correlation between astrometry and photometry is obviously for ZTF, but also for Gaia or LSSC. But it's not only it's not only for resolved sources, for unresolved sources as well. What happens is like this. So you can imagine that if you have it's simple for a double quasar, right? You have a doubly imaged lens. Now you imagine that this one is becoming brighter because of the time delay. But this is unresolved, right? So almost unresolved. What's going to happen is that your astrometry is going to move in this direction. And then your astrometry will going to move in this direction. So there will be a delay on the astrometric light curve from the photometric light curve, a small delay. Right? And based on this, you can actually get candidates even if they're unresolved. If it's resolved, it's easy. The resolved one is the easy case. But actually, we were trying to solve the hard case, because as long as you can solve the hard problem, you can always solve the easy one, right? So,
but the resolved one, actually have to then individually go and say this route.
Yes. Yeah, I can show later. I actually wrote a small code to query ZTF and get everything around a certain position. And we are even trying to get crappy H-knots from it. So, okay. Xray?
Yeah. So I was wondering, a bit away from your talk, more in the hardware sense. So Gaia is roughly a 1.5 meter diffraction limited in one axis telescope. And I'm going to, do some blue sky thinking and said, okay, maybe I have a 4 meter next version Gaia or a telescope, whatever, something like that. Has someone done a forecast of what would such a factor of 2 or 4 increase in resolution mean for the lensing game? And at what point, the systematics, just the very fact we don't understand quasars, the resolve, makes it not very interesting.
Okay, so the question, essentially, Xray was asking so what would be the gain if we had a bigger telescope and not Gaia, like a Gaia with like a factor of 2 inside of the mirror, right, Xray? That's it?
Yeah.
Yeah, so as far as I know, there are no forecasts for this, but obviously we could do a forecast. And the reason why there are no forecasts for this is because we're, so now I'm talking about future of astrometry, right, in general. We're not-
No, I'm not talking for astrometry, I'm just saying imaging, okay? Like, in some sense, I'm just saying, let's imagine a Gaia which is twice as large, 3 times large. What does it do for the lensing? Of course, it'll be amazing, but I want to understand what is the D gain by D cost on this project and whether it's worth it. I'm just trying to get a sense.
Yeah, so in terms, so let's say in terms, if we had a mirror that would be twice as large, supposing that you could do astrometry at the same level, I would imagine that we could get probably astrometry, because for very faint sources, especially at magnitude 20, we're not limited by the Gaia systematics, we're limited by photon noise. So essentially, we would gain in terms of photon noise, and we would be able to actually perhaps get 10 to the 6 solar masses in terms of the deflectors, 10 to the 5.8 or something like that, in terms of the additional clumps. Yeah.
Okay, so we already have ALMA, which has superb resolution.
Yeah.
And of course, unlike Gaia, which almost anything, any quasar is not naturally in the optical, but ALMA it requires a bit more than that. It has an incredible resolution. So
we
the
can't
lens
really hear you. So if you can just ask questions that Alberto can repeat.
Yeah. So Xray, just a quick. Yeah.
I'm saying,
Xray, are you going to be around tomorrow?
Yeah, I can be around.
Yeah. So perfect. We could talk more tomorrow.
Okay.
Perfect. Thanks. So that's a very good question. So he was asking when you're doing time delay cosmography, normally not all lenses are good. You need to select a subset of lenses that are well behaved in a certain sense, right? And he was asking, out of the 44 doubles that we discovered, if all of those lenses are going to be useful or not, right? Or how we're going to select the subset. Okay, so now it comes to the second part of the problem that I was not discussing here, because this is a part of the problem that we are still gathering observations, but we are going to be starting developing more deeply the software now. Our idea is to select select almost everything, including the doubles. So the quads are easier. You are asking about the doubles, but actually the 15 quads that we have, they're probably more useful for traditional time delay cosmography than the doubles, right? This is unquestionable. But what we want to do is actually not to analyze each lens individually. We want to actually create a hierarchical solution that's going to take all the lenses at the same time. Some lenses are going to be heavier in the final solution than the other lenses, right? But all the lenses are going to be analyzed at the same time. We don't want to ignore, like traditionally it has been done in the community. And the other thing is that we also want to profit not only from dedicated observations. So this is what I was mentioning, Matthew, that we have been already getting very bad solutions, but from ZTF data even, right? We want to use archival data as well. There will be targeted data, follow-ups for certain lenses, but we want to use the data for all the lenses. Because especially when you think about the systematics, right? You can have systematics or errors in the modeling, errors in the mass determinations for each one of those lenses. But you should have one H0, or better, one H0 in function of alpha and delta, right? One H0 that is smoothly varying in the sky. Perhaps the variation is zero, it's or compatible with zero. But even when we are modeling, our idea is not to ignore the positions of the lenses in the sky, but to consider as well the positions. Okay. This is another thing that if you wish, we can talk more tomorrow.
Have you thought much about the microlenses problem? They're usually not having multiple images.
Yeah. So I didn't, but this was actually the PhD thesis of this person here. So Jonas Klutter did his PhD with Joachim van Baals in Heidelberg, dedicated to microlensing with Gaia. Yep. Yes, it is to select candidates as well. And one thing that is also useful is to predict events and how you can propagate Gaia in the future. But this is not pure machine learning, but it also involves what you could call machine learning, because everybody calls Gaussian process machine learning, although it's whatever. But you could also use things like Gaussian process to help you predicting the events in the future. Good question. So, so the question is, what type of false positive do you have when we're selecting the candidates, right? In the beginning, in the very early phases of the program. So in the beginning, the real beginning of the program, I started believing that the entropy alone could select good candidates. And in our first run at Palomar, now I think that we observed like 25 targets and we got 3 lenses, which was, well, underwhelming. Yeah, it was underwhelming, right? And then we started to realize, and that's the moment where we realized, obviously the entropy is going to be lower, but a star nearby, we also reduce the entropy, right? Or depending on the scene during the night, if you're using a survey, you are also going to have the entropy varying because of variation on the scene, right? There's a lens that it's barely resolved in the night and it's resolved in the other night, right? And then you're going to have the entropy also following that pattern of scene during the night. So those are things that we have been learning, that we had learned along the time. But in the beginning, we had a lot of stars plus quasars. Now we have much more quasars per, so the doubles, the doublets, the binary quasars, or we have lots of galaxies as well sometimes. Quasar plus galaxy as well. Right? Yeah. Yeah. And the awful thing is that there is a very large number of stars that are projected near quasars for which the y-scholars of the star plus the quasar is completely compatible with being a quasar. So yeah. Yep. You had a question, right?
I had a question. Go ahead. Yeah, so I was wondering about
Yes and no. The thing is that you can, when you read a quantum bit, so, okay, so the question was if it would be meaningful to have, so the x's in this equation, I think that I can use the mouse so people can also see. Yeah, so the x's in this equation are essentially mapped into the state of a quantum bit, okay? And what we do essentially is, when you read out that quantum bit, the quantum bit can live in a superposition state. So it's living in a real, right? But when you read out that bit, it's going to be 0 or 1. So if you read out that bit many times, you can perhaps emulate a certain type of floating point number, right? But one readout is going to be always 0 or 1. So the way that we map this into a quantum computer, essentially, so we didn't have time to talk about this, but the idea is that this Q's here, so this Wasserstein distance is going to be mapped into the superposition state of this quantum bit. Meanwhile, the 2-dimensional projection of the Wasserstein distance is going to be mapped into the likelihood of the quantum bits I and G being entangled. So essentially, that's how you create the quantum system that then you're going to be essentially programming into a quantum computer to find the minimum state of the Hamiltonian. And obviously, Wasserstein distances are big, so this should be mine of the Wasserstein distance, not the Wasserstein distance. Yeah, it is.
all right, so
Thank you.